Okay, in this lecture, we will be looking at population proportions and how to construct confidence intervals and how to test hypotheses on population proportions. So we will be taking samples and using the sample statistic to infer something about the population proportion. So the first thing that you need to know about this topic is that if you start with any binomial distribution with n number of trials or sample size, you can think of it, and probability of success p, then there is a condition under which this binomial distribution can be approximated by a normal distribution. Remember that the binomial distribution is a discrete distribution, and what we're doing now is we are approximating it with a continuous random variable so that we can apply the central limit theorem and get a result on the sampling distribution of the sample proportion. So first thing I will do now is I will let you see the binomial distribution and the normal distribution that will approximate it eventually. And notice that I put here the normal distribution has mean mu is n times p, the mean is np, and you know this from the discrete binomial distribution. In any binomial distribution, the mean is n times p, and the standard deviation is this radical of n times p times 1 minus p. So I'm going to leave both of them here, and you can see that here n is 1, and I chose the probability of success to be 50%. What I would like you to do now, as I increase this n, look at the graph on the right side, and also at the same time keep an eye on np and n times 1 minus p. We want both of them to be at least 5. So keep an eye also on these numbers. Right now, both of them are 0.5, because you can think of this as a coin flip where the probability of heads, let's say success means that you get heads. Probability is 50% heads, 50% tails for a fair coin. And when you flip it once, look at the graph here. It's only the two dots there that 0 heads has probability 50% and 1 heads has probability 50%. That's if you're thinking about a coin flip. And the only reason I mentioned it is because we put p to be 50%. So now I'm going to start increasing n, and you will keep an eye on the graph and on both of these. And when they reach, both of them reach 5, we will see something interesting happening. So I'm going to superimpose the normal distribution that I told you about. This is the one that we will use to approximate our binomial distribution. So the binomial distribution is the discrete one, and it's the one that has the dots that you see here. And the normal is the blue. Don't forget this. Now I will play n. Notice that now 2.5, 3, 3.5, 4, 4.5, 5. Okay, so we can stop, of course, when it was at 10, we reached, both of them reached 5 already. And look here, the approximation is really nice. Okay, first take the normal distribution off. You'll see that when the probability of success is 50% in a binomial distribution, remember that we saw it will be precisely symmetric. And as p goes down or up from 50%, it becomes skewed. So if p is less than 50%, it's skewed like this, and if it's more than 50%, it will be skewed like this. Okay, so now keep it at 50. We reached 5, and we saw that the normal distribution is a very good approximation. Now, the problem is, in most cases, we don't have 50%. We usually get things that are not 50%. So what if, for example, we had 30%? Okay, then look here, np and n1 minus p. We need both of them to be more than 5, but still we need to increase n so that we reach this. So I'm going to play and increase n. Look, until we reach 5. And you watch NP 3.9, 4.2, 4.8, 5.1. So when n is 17, we reached that both of these are more than 5, and you can see that the approximation is very good. Now, I should tell you something, is that in most textbooks, they require this number to be at least 5. How do you think about it? Remember that this NP for a binomial distribution, this was the expected value or the mean of the binomial random variable. And so this also we saw it was the expected value of x, which is the expected number of successes. Here you can say this is the expected number of successes. And remember, you define what success means in your experiment. Because your experiment is binomial, it has 2 outcomes. You choose which one of them you will call success. Okay? And the expected number of successes, we are saying, should be at least 5. Should be at least 5. But not only this, we need also n times 1 minus p to be at least 5. So you can say not only that the expected number of successes should be at least 5, but also and failures. So you need at least 5 successes and 5 failures in your experiment in order to be able to use the normal approximation to this binomial random variable that you started with. Now, in the 1990s and early 2000s, people started requiring this number to be higher. So they used 10. And currently, these days, there are even some researchers that use 15 as the minimum number of successes and failures. The least number of successes is 15 and the least number of failures 15. Notice that this means that n itself must be at least 30 because you want 15 successes, 15 failures. And of course, if p is exactly 50%, you will reach exactly 15 here and 15 there. Okay, but most of the time p, you cannot rely on it being 50%. So what we're saying here is that currently any sample should be 30 or more. That's what people are agreed on. Okay, but in our textbook, just to make it simpler, and also it works. The thing is, it works. I showed you in Dismos that it's a good approximation. So in our course, we will use this number 5. I just want to tell you something. When you say that n times p should be more than 5 and n times 1 minus p should be also at least 5, in fact, if you think about it carefully, let's say that p is the smaller of the two. Like, let's say that p is 20%, then 1 minus p will be 80%. And if n times, if 20% of n is at least 5, then immediately this will be satisfied. So what am I trying to tell you is that this condition, actually, you can write it in a nicer way to say that n should be bigger than or equal. Look at this. You can write it first like this, 5 over p and n also bigger than 5 over 1 minus p. If you want to combine them into one, look at how beautiful it is. You can say n is bigger than or equal to 5 over the minimum of the p and 1 minus p. If you understood what I said, then this will be your condition. You can combine them into one, okay? Because if there is a way to make sure that if one of the two inequalities is satisfied, then the other will be satisfied automatically, because we have p here and they're also 1 minus p, they're related. Good. So now let's erase this and talk about the following, is that we start with a binomial random variable with n number of independent trials and probability of success p. Remember that some people use q to be the probability of failure, yes, but it is the same as 1 minus p, and it's better just not to include more letters when you are doing computations. So what I mean to say is this: then we know that the mean of this binomial random variable is n times p, and the standard deviation of a binomial random variable is the radical n times p times q. But instead of q, I like to write it as 1 minus p in order to see less variables in your formula. So notice that these two, this we studied when we were looking at discrete random variables, and the most basic example and the most important example of a discrete random variable is the binomial. So these are things that you should know by heart, okay? Now, what we want to do is use the condition. So if we are sure that np is bigger than 5 and n1 minus p is at least 5, then we can do a lot of things. So first thing is, what is the mean of p hat? What is, well, p hat first is x over n. So this sample proportion, how do you compute it? You take the number of successes divided by the sample size that you took, keeping in mind that you should make sure that these two conditions are satisfied. And then this here will have a distribution, the sampling distribution of the sample proportion. So this distribution is going to be a normal distribution, approximately, of course, approximately normal, with mean p and standard deviation radical p times 1 minus p over n. Of course, you will ask, where are these coming from? Look at the following. So we said that p hat is going to be x over n, okay? So now, what is the mean of x over n? Remember, x was binomial, and you can take any constants outside. It's linear in x. So this will be 1 over n, and remember the mean of a binomial is n times p, and so the n cancels the n, and you end up with p. So in other words, actually, you can write it this way. You can say the mean of the sampling distribution of sample proportions is the true population proportion p, and the standard deviation of p hat is the standard deviation, of course, of x over n. You can take the number outside, the 1 over n, and you get sigma x. Now, what would this be? 1 over n, and remember, the standard deviation is n times p times 1 minus p. And we'll continue here. So this is 1 over n, or actually you can combine them. So you can do it like this: radical n p 1 minus p, and instead of n, you can write it as radical n squared. It's positive, you can do that. And so this will be radical n p 1 minus p over n squared. And the n cancels the square, and you end up with what? Radical p 1 minus p over n, which is what we have here. So this explains to you where the mean and standard deviation of the sampling distribution of the sample proportion comes from. Where do these formulas come from? So now you know where they come from. What I would like to do also is this. We will solve examples in just a little bit. But for now, check what Lanud is telling you. She's telling you we can apply this theory to find probabilities involving sample proportions. So let's see an example, and understand things better. Suppose it is known that 62% of residents in Abu Dhabi own an iPhone. So in this case, the true population proportion is 62%. Okay, this is something that we, let's say, know. Okay, it's known in this case. Usually, this is unknown and you want to approximate it. That's when you construct confidence intervals. And you can also test hypotheses about this P to check if it's an accurate proportion or not. But let us assume that this is an accurate proportion for the entire population of residents in Abu Dhabi. So now we took a random sample of 50 residents. So N is 50. And what else? They were surveyed. What is the probability? So they're asking, what is the probability that the proportion of the sample, remember, the sample proportion, we write it as P hat. So this is P hat is X over N. This is the sample proportion. So what is the probability that the sample proportion, P hat, is between 60 and 65%? This is the question. So you want, what is the probability that if you take a sample of size 50 and find how many people in this sample have an iPhone and divide it by the total number, it's kind of a mean in some sense. This proportion, you can think of it as a mean, and that's why the central limit theorem worked. To give you the sampling distribution of the sample proportion, and we were able to compute the mean and standard deviation for P hat, the sampling distribution of P hat. And so in this case, how do you go from P hat to Z? There is this formula here that takes you from P hat to the Z score. So actually, this is the same as what we did before. If you remember, the Z score was X bar minus mu over, if you remember, sigma over radical N. But in that case, we had what? This mu was the mean and the mean of the population mean, and this is the sample mean. So the same way, this is the sample proportion, and this is the population proportion. And then you divide by the standard deviation of X bar in this case, which is this, and this one here was just the standard deviation of P hat. You see how nice it is? Because these are related things, okay? But I would like to draw your attention to another fact. First, let us solve this example, and then I would like to solve it in two ways so that you see something interesting. So first, how would we find it? This, you just go from P hat to the Z score. So how do we do this? This will be the probability, and you will do P hat minus P over radical P times 1 minus P over N. This is, of course, this is your Z score here. And I got this formula just from the previous slide. Okay? And you want to do this computation, so you'll get 60 minus, now what is P? We have it 62% over radical 0.62 times 1 minus 0.62 is 0.38 over 50. And here the same thing, but you will put, because you want to go up to 65, you'll put 0.65 minus 62 over the same radical. So this times this over 50. Okay, so now what I would like to do is find this one and this one on my calculator so that we can compute the probability. So now we open the calculator and we will compute the first one. We can make it just a little smaller. So here, 0.60, I'm computing this now, okay? 0.60 minus 0.62 divided by radical and then you multiply 0.62 times, and you can say 1 minus 0.62 divided by 50. And so this is, and we take it, let's say, to 2 digits, as we always do with z-scores. So this will be the probability that the z-score is between negative 0.29, and the other one is very simple, just this 60, change it to 0.65. And so this will be 0.44 if you want to 2 digits. And now, what do we use? We're going to use our online calculator to do it. So let's go there and set the things here. So since we are using the z-score, this makes us able to leave the mean and standard deviation as 0 and 1. And so we just want to say between, let's see, between what and what? We will look from here, between minus 0.29 up to 0.44, and calculate. Yeah, so you see the calculation here, and actually you can see the graph also. So we wanted this probability, so it was this area that is shaded black, and this probability is 0.2841, okay, which is 28.41%. But what does it mean? It means that if you take a sample of size 50, then the probability that your sample proportion will lie between 60 and 65% is about 28.5%. You can say that. Okay, so just remember this number and the way we solved it, and now I'm going to show you another way to, maybe we keep this, it doesn't hurt. So what you can do is say this, well, what is the sampling distribution of p hat has mean? The mean of this is p, which is 0.62, it's given, and the standard, this is the mean of p hat, of course, and this is the standard deviation of p hat, is the radical p times 1 minus p over n. By the way, when you are constructing confidence intervals, remember that you are going to, you cannot use this standard deviation because it has a p here and p is unknown. So this is why we replace this. So while computing, it's important that I mention it now, while computing confidence intervals for the population, true population proportion p, we use instead, look at what we will do. Instead, we will say the standard deviation of the sampling distribution, because we don't know p, but in our sample gave us p hat. So this is why you see p hat there. So we replace p by p hat, even though it's wrong, it's not the right formula, but we don't have any other choice but to replace it. Okay, this is very important remark. But if you know it, if you had the privilege of knowing p, then of course you wouldn't be looking for it if you know it, but then you can get exact answers, precise answers. So in our case, let's compute this. So this was, in our case, 0.62. Let me write it in a place where you can see it really. So this will be radical 0.62. Remember, 0.62, they gave it to us at the beginning, and we know the sample size is 50 from the beginning. So 62 into 1 minus 0.62 over 50. How much would this be? So what we will do is go to our calculator, of course, and find it. So let's do it on the calculator, radical, and then a fraction, 0.62 times 1 minus 0.62. Okay, you don't even need to put multiplication, it understands it, over 50. So our standard deviation is approximately 0.0 0.0686. Let me take 4 digits. And now look at how beautiful this will be. Since you already, so now I will write them here better, yeah? So your mu is P, which is 0.62, and your standard deviation is 0.0686. Remember these numbers. Let me highlight them so you look at them now when I'm using the calculator. And remember, they asked us to do this. So here, we go back to the calculator, and now, of course, you're computing probability. So I remind you, you do area from a value because you're giving a value and you want the probability. So here you will put the mean as what we have here, 62. This 0.62. And the standard deviation is this one, 0.0686. And we want between, remember, between what and what? Yeah, between 0.060 and 0.65. And now we will calculate. See, what did we get? You remember our previous answer, 28.41? We got almost the same. And of course, because we just used some approximations, that's why the answer was a little bit off. But if you take it to 2 digits, it will be the same. It will be 0.28. So you can say that this means that what we found means that this question mark is no longer a question mark, and the right answer to this question is 0.2837, which is okay. Whichever method you use, you are getting very close answers. So this will be 28.37%. Use whichever one you like in order to compute probabilities. So this is actually computing probabilities is not included, but it's important to see it so that you know how to change to the Z-score. Because actually you see this Z-score that you have here. This would be your test statistic when you are doing hypothesis testing for population proportion. And the only difference is that, so if you watch the lecture on hypothesis testing for the population mean, it is exactly the same thing, but your Z-score will be P hat minus P0, and here you'll put also P0. And this P0 is the number you get from the null and alternative hypotheses. Remember, the null hypothesis could be, for example, P is equal to P0, and in this case, the alternative will be P is not equal to P0. So this is the one that you are putting in the formula here when you do hypothesis testing, okay? And everything else is the same. One advantage and something very nice about population proportions when you do statistics is that you always use the Z-test. There is no t-test at all when you do population proportions, okay? The reason being that you are actually working with normal distributions. Remember, when our condition is satisfied. Oh, by the way, did we check that our condition is satisfied here? This is something that you need to check. So it's good that I didn't, so that you see that, okay, it's not a mistake, because when I made this example, or yeah, I chose numbers that would work, but you cannot solve it immediately. It's better that you start like this. When you are solving this question, you'll just make sure that NP and N1 times 1 minus P both are more than 5. So look at this here. We have N is 50 and P is 0.62, so 31, that's good. And also we can do 50 times 1 minus 0.62, 19. Both of them are more than 5. In fact, both of them are more than 15. So we can be current with this, like we are like using what they are currently using, because we had that the smaller of them is 19. So this means that it will be a very good normal approximation. Okay, and for confidence intervals, that will be the last thing that we do. For confidence intervals, for the true population proportion P, all what you have to do is, okay, take a sample of size n. Look at this. This is the process. It's good. I will describe the process without a specific example, because if you understand the process, you can solve any example. So take a sample of size n, and then, so that's your first step in order to compute confidence intervals for population proportion. Second step is, define what success means and find p hat. So p hat will be how many successes you have over the sample size. But here, when we say successes, you can think of an infinite number of examples. What you are looking at right now is something that can be applied in many situations. In voting, for example, if you want to check the percentage of votes for a certain candidate, you can use exactly what I'm doing now. So you will take a sample of size n, and you will find p hat, the number of successes over n, and now make sure that n times p hat is at least 5, and n times 1 minus p hat is at least 5. Okay? In our textbook, we use the minimum to be 5, and so you don't have to make it 10 or 15. It's okay. 5 or more, but both of them have to be at least 5, as you remember. So after you find p hat, then what level of confidence do you want? So if you remember, so for example, if we say the confidence level is, we want 90% confidence, then this will mean that the significance is 1 minus the confidence, which is 10%. And if you remember, in this case, the critical value Z alpha over 2 will be 1.645. And if C is 95%, if you want to be 95% confident, then alpha will be 5% in this case. And if you recall, this is like the most used number in statistics, because we use 95% confidence intervals a lot. This will be 1.96 for 95% confidence. And if you remember also, for 99% confidence, alpha will be 1%, and Z sub alpha over 2 is around 2.50 something. Let me put 57 and then go check if it's true or not, and then we'll come back. Okay, so you will just, I will just refresh so it comes back to how it was, and we want value from an area because we want the Z. So the area is what? Now for example, when you want 0.01, that will be the significance level, and so you will say outside 2.576. 576 actually. So after the 7 there is 6. So if you want to 2 digits, you need to put 8, 2.58. Okay. Or remember, if you want to put the confidence level, which is 99%, then it has to be between. And so you will take the positive Z as your critical Z score. Okay. And so these are the steps. So that is number 1, number 2, number 3, and now number 4, the last one. Well, let's keep going. I'll do 5 steps instead. Compute the margin of error. Okay, E, we call it E. What is the margin of error in this case? It's just the same as what we did before. Z alpha over 2 times, if you remember, it was sigma x bar when we did what? The confidence interval for the population mean. And that was, if you remember, it was also sigma over radical n. But now we need sigma p hat. And this will be, let's write it next to it to have more space. So this will be Z alpha over 2 times, if you recall, that was radical P, the true population proportion, times 1 minus P over N. But as I told you, since P is unknown, we are trying to construct a confidence interval for it, so we don't know it. That's why here you see in the formula you will put P hat and take it as your sigma of P hat to be this, even though it's not the correct exact value, but you don't have any other choice. Okay, so this is the margin of error. How about this? Well, for this I'll put it in red and the other one in green, Z alpha over 2, and then the entire thing, let's do it in purple. Like this whole thing is the margin of error. Notice that in many examples you will be given, in any example you must be given all of the variables except one. So then we ask you to do it. So sometimes they ask you to find the sample size and they give you the margin of error and they tell you what level of significance we want so you can compute the critical value. You see? So it depends on the question. Each question would ask something, but all of them cannot ask more than finding one of these things. Okay? It could be find the margin of error, find the sample size. Okay? At the end, what do you do? In step 5 now, once you have all of these things in your hand, you will construct the confidence interval. So you'll put your p hat in the middle of it, and then the lower confidence limit will be here, and the upper confidence limit will be there. So this is the lower confidence limit, and this is the upper confidence limit. And what are they? The lower confidence limit, I'll write the formula here, and the upper will be just with a plus instead of a minus. So it will be p hat minus, you can say just minus e. And this here is p hat plus e. And so if you want to write the entire thing, you say p hat minus z alpha over 2 sigma p hat, if you want it to be a little shorter. But you can also do the entire thing and write it. So you can say p hat minus z alpha over 2. And then what is sigma p hat? It's radical p times 1 minus p over n, but because we don't know p, we'll use p hat. And for this, you'll put a plus for the upper confidence limit, and you're done. Remember that p hat is exactly in the middle of this interval. Okay, and I told you for hypothesis testing, the only thing you'll do is just put the p0 here and the p hat you got from your sample and your sample size. This will give you what? The z statistic that will give you the p-value so that you can test the hypothesis, just like we did for testing hypothesis of the population mean. So I hope that this helped you understanding differences and similarities between confidence intervals for population mean and confidence intervals for population proportion, and also how to test hypotheses. You saw that they are almost the same, but there is an advantage of the population proportion when you test hypotheses, is that you always use the Z test. There is no T test in this case, so it's much easier. And also, these formulas will be given to you during the assessment. So no need to memorize. It's important that you just understand this topic. And I will stop here.